Hello dear students, in this subject groundwater assessment and development, today we'll start a new chapter, that is well hydraulics. Okay, so in this chapter first we'll discuss about the well hydraulics. That means the flow characteristic when there will be groundwater flows into the well means when pumping is carried out through the well, how the uh, how flow occurs, that will be studied first. Then we'll discuss about the different test, pumping test, water wells test holes, well-as methods of drilling of deep wells, cable tool drilling method, rotary method, pumps. Okay, all these things that will be discussed after that. So in today's class, we'll discuss about this well hydraulics. Means how the flow occur when there will be flow between the groundwater to the wells. Okay, when we are pumping the groundwater through the wells. We know the well is the most important method of groundwater extraction. Okay, consider the water in an unconfined aquifer being pumped at a constant rate from a well. Okay, let's consider a confined aquifer first. A pumped at a constant rate from a well. Prior to pumping, the water table in the well indicates the static water table. Means here you can see in this first page there is no pumping. Pumping has not yet started. So here there is static. The water table level is static. Okay, this level is static. When pumping starts, what will happen? There will be drop of this groundwater table. Okay, there will be groundwater table drop. The level drop. The groundwater level reduces. Means due to the pumping, there will be accelerated flow near the well. Means here, when pumping occur, there will be the flow towards this well increases gradually. When you start pumping, then flow will start. Means water will flow towards this well, and it may reverse groundwater flow. Means in some cases, let water is flowing in this direction. Okay, before pumping, but before pumping is moving in this direction. Okay, after pumping, what will happen? Then it will reverse. This direction will reverse. Okay, this direction will reverse. Okay, this direction will reverse. In this direction, it will start to move. So it causes a water table drawdown. There will be water table drawdown. Okay, and it will be maximum near the well. And if you go away from the well, it decreases. The drawdown decreases. Okay, so this is called drawdown. It forms a cone of depression. This curve is called cone of depression. This cone is called cone of depression. So let's talk about these different important terms. First, drawdown, cone of depression, area of influence, radius of influence. That let's discuss. Drawdown means the drop of water table elevation from original water table in well due to pumping. This was your original water level. Okay, water table level, and when after pumping, the level decreases. So this drop, okay, at this point, these are the observation wells. These are the observation wells, 2 observation wells to record the drawdown. So in this well, this is the drawdown, and this well, this is the drawdown. Okay, this fall of this water table is called drawdown. Cone of depression means this curve. The conical shaped depression of the water table around a pumping well caused by the withdrawal of the water. By the withdrawal of water, there will be the shape of this water table. Okay, the shape of the water table changes. So this curve is called cone of depression. Area of influence. The areal extent of the cone of depression. The areal extent of the cone of depression means this area. It must be a circular area. Okay, it must be a circular area. Okay. Okay, this circular area, this total area is called area of influence. Radius of influence, maximum horizontal extent of the cone of depression when the well is in equilibrium with the influx. Okay, first when there will be pumping, when pumping started, there will be decrease in level. Okay, after some time, what will happen? Okay, there will be decrease and there will be the aerial extent will increase gradually. There will be aerial extent will increase. After some time, what will happen? The inflow into the groundwater, or you can say recharge to the groundwater will be same as the pumping discharge. The water which is we are taking out, means the pumping discharge will become same as this water joining this water table. The inflow into the groundwater table. Okay, so this inflow into the groundwater and the discharge which are taking, okay, this I will be equal to Q after some time. Okay. So at that point of time, when this Q becomes I, discharge means outflow becomes inflow, what will happen? This aerial extent will not increase more. So the drawdown will not increase more. That will stop. The drawdown will stop and this aerial extent will stop. Means that is called equilibrium condition. So initially what will happen when pumping started? The Q is more than I. Okay. Means the water which you are pumping, that will be more than inflow into the groundwater. The Q will be more than I is less. Gradually, after certain point of time, the I will become equal. This I will become equal. Okay, here I is less than Q. Okay, at this point of time, when I is equal to Q, this is called equilibrium condition. So after the well attains the equilibrium condition, there will be no more increase in aerial extent. This aerial extent, okay, this aerial extent will not increase. There will be no more drawdown. Okay, so this cone of depression will remains constant. This curve will remains constant after that. Okay, so this maximum horizontal extent. This is the maximum. This is the maximum horizontal extent. This is the center. This is the maximum horizontal extent. That is called radius of influence. So this maximum horizontal extent of the cone of depression when the well is in equilibrium with inflows. Okay. Next is there will be different flow, steady flow and unsteady flow. Steady flow means the flow in which the piezometric head or the water table level does not change with time. That is also called equilibrium state or equilibrium flow or equilibrium condition. That I told that when I become equal, I is equal to Q, there will be no more drawdown. It says that the well attains the steady state condition. That is called steady flow. Okay, that means the well attains the equilibrium condition. That is called steady flow. The piezometric head does not change. Means that the piezometric head means here at this point, if you insert a piezometer, at these observation wells, here you insert a piezometer. This is called this depth of water. At that point is called piezometric head. This is called piezometric head. So this piezometric head will not change. Okay. Unsteady flow in which the piezometric head changes with time. So remember, when the pumping starts, then the unsteady flow first it will occur. First there will be unsteady flow. There will be decrease of this water table, means there will be drawdown, and there will be the gradual increase in this cone of this depression, and there will be gradual increase in this aerial extent. Okay. After a certain time, then when I will be becoming equal to Q, then there will be no more changes in this drawdown curve or cone of depression. So that is called steady state condition. So initially there will be unsteady flow. After that, there will be steady flow. Here you can see at the constant rate of pumping, the drawdown curve develops gradually with the time that I talked about. That is the unsteady flow. That is called unsteady flow. During at the constant rate of pumping, the drawdown curve develops gradually with the time. Okay, this phase is called unsteady flow as the water table elevation near the well changes with time. Near the well, the drawdown changes, the water table elevation that changes. Okay, so that is called unsteady flow. So initially unsteady flow occurs. On prolonged pumping, okay, an equilibrium state is reached between the rate of pumping and the rate of inflow of groundwater. Means the rate of pumping will become equal to rate of inflow of groundwater. The drawdown attains a constant position with respect to time. Okay, the drawdown attains a constant position with respect to time. Means with respect to time, the drawdown will not change. Okay, that will occur after certain point of time. At a certain point of time, and the well is said to be operate under steady state condition. Okay, so at steady state, we can say this is the maximum extension. This is the maximum extension, and the drawdown, this drawdown will be maximum at the well and at the different points that we can say maximum. Okay, and the head, the piezometric head means that at this point the piezometric head is H. Okay, that will not decrease further. That will remain constant at steady state. Okay. Here you see in the three stages: initial stage, intermediate stage, steady state stage. So initial stage, this is the flow line. These are the flow line. Okay, these are the flow lines. This is the well. Now there is no pumping. Now there is no pumping. Okay, this is the groundwater table. Okay, and when pumping starts, intermediate state, when pumping starts, then there will be drawdown here near the well, and it will extend, and this is the cone of depression. So this is called depressive flow lines. The flow line will depress here. The flow line, you can see it will depress. So this will be your new groundwater table. So this depressed first flow line of this depressed groundwater table. Okay, this curve is called cone of depression. And after a certain point of time, there will be maximum drawdown. It means there will be no more drawdown. And here the inflow I becomes equal to Q. Here I was less than Q. Here Q is 0. Okay, here I is less than Q. Here I become equal to Q. That means it attains here equilibrium condition. Okay. And here it said that here it is unsteady. Initially there will be unsteady flow. Here will be steady. Here there will be steady flow. That's called steady state condition. If pumping continues, more water must be derived from the aquifer storage at greater distance from the pore of the wells. And the following items are observed. The cone of depression is expanded. The radius of influence of the well increases due to expansion of the cone. The drawdown is incremented at any point with increase in depth of the cone to provide the additional head required to move the water from greater distance. That means the H1 on H2 means the head that increases. When cone of depression increases, when the aerial extent increases, this head, okay, the drawdown is incremented at any point with the increase in depth of the cone. This is the depth of the cone. The depth of the cone increases. The depth of cone increases. The head decreases. Okay. Here this is the level. Okay. This will be your piezometric head at different points. The piezometric head decreases, but this height of the depth of the cone increases. The cone expands and deepens more slowly with time. The cone expands and deepens more slowly with time. So now we can say there will be different cases. One is steady flow confined aquifer, steady flow unconfined aquifer, unsteady flow in confined aquifer, and unsteady flow in unconfined aquifer. So these four cases we will discuss. Okay. So today we will discuss about this steady flow and confined aquifers. So these are the basic assumption is taken when the analysis is carried out. The aquifer is confined. Okay, so here we are discussing the steady flow and confined aquifer. So aquifer is confined. Aquifer has infinite aerial extent. Infinite aerial extent. There will be no resistance to this aerial extent. Means there will be no blocking. The aquifer is homogeneous, isotropic, uniform thickness. Uniform thickness is considered. It's homogeneous and isotropic. The piezometric surface is horizontal prior to pumping. Piezometric surface is horizontal before the pumping. Okay, it is horizontal. Groundwater level is horizontal before pumping. The well penetrates the full thickness. The aquifer is pumped at a constant discharge rate. The pumping rate is constant. Pumping rate is not varied. That is constant. That is not. Q is constant. It's not changing with respect to time. The well penetrates the full thickness of the aquifer. Here this is the aquifer, confined aquifer. This is the confined aquifer. This is the confined aquifer. Okay. Here the well penetrates fully. That assumption is taken, not a half. Okay, it is fully penetrates to the confined aquifer. That is the assumption. The well penetrates the full thickness of aquifer and thus receives water by horizontal flow. There will be horizontal flow. Okay, isotropic and homogeneous, that already we discussed, and at all direction it is same. The hydraulic properties in all direction and at all points are same. Okay. Here you can see this is the drawdown curve. This is the well. Okay, and let drawdown at some distance. Okay, from the well is S. This is the RW is the radius of the well. 2RW is the diameter of this pumping well. H1 and H2 are the piezometric head corresponding to drawdown H1 and H2 at two different points. The maximum depth of this maximum piezometric head, which is occur at this extreme point, that is capital H. This is the confined aquifer. At the well, the drawdown is SW and piezometric head is HW. The thickness is B. The aquifer thickness is B and discharge is Q. The figure shows a well completely penetrating horizontal confined aquifer thickness B. Consider the well is discharging a steady flow Q. The original piezometric head is H. The drawdowns due to pumping are S1 and S2. S1 and S2. And at the pumping well, piezometric head is HW and drawdown is SW. Okay. So here you can see the confined aquifer steady state radial flow to the fully penetrating well being pumped is shown in here in this figure. The well discharge is Q at any radial distance R from the pumped well is equal. The discharge is set at any radial distance from R from the pumped well. From the pump at any radial distance, the Q is same. Let's see here two radial distance is taken, R1 and R2. This is R2. This is R1. This is R1. This is R2. Okay. So for this R1, the S1 is drawdown, okay, and H1 is the piezometric head. And for the R2, okay, R2 cone of depression, the S2 is the head drawdown and H2 is the piezometric head. But increasing the radial distance from the well increases the area of discharge. Okay, by increasing the distance from the well, means from the well, if distance increases, this distance increases, means R1 becomes R2, its areal extent increases. The area of discharging increases. So when area discharge increases, what will happen? Since Q is the same, here Q1 is equal to Q2. Q1 is equal to, you can see here, Q1 is equal to Q2. So, but A1 is equal to the cylindrical portion. This is the cylinder, you can say. The cylindrical area is A1 is equal to 2 pi R1 into B. Let B is the thickness. So 2 pi R1 B, A2 is the 2 pi R2 B. So B is the thickness. So this is the thickness, maximum thickness of this aquifer. Okay. And so velocity is inversely proportional to the area. So if area increases, the velocity decreases. So the flow velocity decreases. The surface is flatter. Okay. If you see the surface, this surface is flatter. Piezometric surface is almost static. Piezometric surface is almost static. Means it attains the static condition, or you can say steady state. So at a radial distance r from the well, if h is the piezometric head, then by Darcy's law, the velocity is v is equal to k into dh by dr. The cylindrical surface through which this velocity occurs, okay, the cylindrical surface, okay, is 2 pi r into b. If r, if you take at a certain point, at this point, if you consider r is the distance, r is the distance from the well or radius of this cone of depression, and so area will be 2 pi r and the thickness is b. For this thickness, we are talking about this thickness. This is the thickness. So cylindrical area will be this 2 pi r and circumference is 2 pi r and b is the thickness. So 2 pi r b. The discharge entering the cylindrical surface to the well discharge is q is equal to ab. So discharge will be equal to this discharge which you are pumping out is area into velocity. Means the discharge which is joining to this well is equal to q. So that q will be equal to area into velocity. So Darcy's velocity if we use and the area is 2 pi r b, then this will be q by 2 pi kb dr by r equal to ds. So if we integrate between limits r1 and r2, let 2 points were considered, r1 and r2, with the corresponding piezometric heads h1 and s2, then it will be q by 2 pi kb ln r2 by r1, which will be equal to s2 minus h1. Hence the equilibrium equation for the steady state flow in a confined aquifer will be q is equal to 2 pi kb into s2 minus h1 divided by ln r2 by r1. So this equation is called Thiem's equation. So this is the general equation of the Thiem. This is also called Thiem's general equation. Okay. So integrating with boundary condition, if we put different boundary conditions, okay, like at extreme the area of extent, okay, radius of influence, you can say. If we put different boundary condition, we'll get different form. Okay, this is the original equation. Different forms of this equation can be obtained. So at the edge of the zone of influence, this is the zone of influence. At the edge of the zone of influence here, H2 is capital H, means this is the piezometric head, and R2 is capital R. That is the radius of influence. R2 is the radius of influence. At the pumping well, if you see this point, at the pumping well, here H1 SW is the piezometric head and RW is this is the center axis of the well. So this is the This is the radius of the well, Rw. So if this two case here in this general equation, we'll get 2 pi t. This kb is nothing but t. Okay, kb is nothing but t. Transmissibility we put, then h minus sw divided by ln r by rw. Okay, this is one equation. Then another equation we can put here. If you draw down S1 and S2 are the observation wells are known, and noting that S1 is equal to H minus H1 and S2 is equal to H minus H2, means two observation wells, this one and this one, two observation wells, and here the drawdown is S1 and here S2. So this S1 will be equal to total capital H, this total piezometric head minus piezometric head is here H1 and here H minus H2. Okay. If you put here, then this will be 2 pi t into S1 minus S2. Okay. Here it was S2 minus H1. So you can put these two. Okay. This we can put these two in place of this H1 and S2. Or if you put H1 is equal to how much? S1, yes, capital H minus S1. And H2 is equal to capital H minus H2. So in place of H1 and S2, if we put H minus H1 minus of H minus H2, we'll get 2 pi t into S1 minus S2 divided by ln R2 by R1. Okay, this is one form of the equation. So here at the edge of the influence, if H2 is equal to capital H and radius of influence is capital R, and here drawdown is 0. Okay, at this point drawdown is 0. At the pumping well, the HW is the zone of this piezometric head. RW is the radius of influence, and here SW is the drawdown. So here the maximum drawdown, that is S1, okay, sorry, SW are the well point we consider, then that equation can be modified into this form. This is S1, S2, this is the S1 minus S2. So this you can write SW minus 0 divided by ln R2 by R1. So it will be R by capital R by RW. So these equations, okay, these two equations can be used to predict this transmissibility and hydraulic conductivity K. Okay, so these three equations, total 4 equations, this is the original equation and these are the 3 modified equations. These equations can be used to calculate discharge and transmissibility and hydraulic conductivity. If we have the discharge data, pumping how much the discharge we are pumping, that data we know, if we know, then we can calculate this T and hydraulic conductivity. Okay, so this much for today's class. Okay, next class we'll solve problems on this topic. Okay, thank you so much.